Hi everybody, welcome to Test 2 review for pre-calculus. We will go from section 4.1 to 6.3, and as always, the topics are on the top, and when we finish a topic, then I'll draw a line through it, and then we just move on to the next one. With that, you can keep track of where we are on the video. Right, I'll just look at take a look at the first topic. Computation. So pretty much we just do something like this, and then the domain of the computation, we still need to find the computation of the two functions. Anyway, so the first one, computation of this. So the question asks us for the function g of f of x. So that the second function is the inside function, so it is g of f of x. Now we look at the g function is the outside one. It is 4x plus 9, so let's say g is 4 times something plus 9. That is the function g. And then inside, instead of x, we're going to have f of x. And then f of x is equal to x minus 9 over 4. And then plus 9. 4, I'm sorry, this 4 and this 4 cancel out. Have x minus 9 plus 9 and 9 cancel out as well. We have x. So just something like this, meaning we're going to put the second function into the x of the first function here. Yeah. So the second function is the inside function, and that's what we have. Right. Next, we find the domain of the computation of f and g. So first I write out the rule. Domain of the computation is domain of the second function, in this case g, intersect with the domain of whatever we get at the end. This might look the same, but in order for this to exist, we need the g to be defined as well. So we'll see. I should put an x here so that's less confusing. But anyway, first we find f of g of x first. So f of g. So first, focus on the outside function. Function f is something over something plus 9. That is the function f. Now that something is g of x, which is 18 x plus 1 and 18 x plus 1. Right. To simplify this, we only have the fraction top and bottom, but only has x plus 1 as the denominator. So we multiply that top and bottom. So multiply it out. We have x plus 1 cancel, so just 18. And then x plus 1 times x plus 1 here is 18 plus 9 times x plus 1. So we have 18 over 18 plus 9x plus 9 and 9x plus 27. Right, so that. So we found the computation of f and g. Right, now we go back to the problem. So the domain of this is going to be the domain of g, the second function. So this second function is 18 over x plus 1. The domain of that is where the denominator not equal to 0. So the domain of the function g is going to be equal to x plus 1 not equal to 0 intersect with the domain of the result. So this is, if it is confusing, consider whatever this is the end result of the computation. And we have 9x plus 27 not equal to 0 because that is the denominator. Cannot have that. And put this together, we have x not equal to negative 1 intersect with x not equal to negative 27 over 9, so negative 3. So x is not equal to negative 1 and x not equal to negative 3. So we have the domain. Yeah, we can write like that. Or on the number line. Or interval notation. So pretty much you can write like that, x not equal to negative 1. Actually, it's better to say it. And x not equal to negative 3. So x not equal to negative 1 and x not equal to negative 3. Or use the interval notation. Or use the graph. This, or this would be acceptable. So yeah, any of this 3 is acceptable. Right, let me update the list. So we done the first part, computation of function. It could be either this or this. And the domain of the computation is this in red. So we have 2 and 3. Right. So yeah, I update that list. Right. Next, find the inverse of a function. So the inverse of the function, the fundamental thing is that we're going to interchange x and y, or interchange the domain and the range. So because of that, we just interchange the x and y, and then when possible solve for y. So I write the two important steps to find the inverse. So to find the inverse, there will be two steps. The first one is to interchange x and y, and the second step is to solve for y. Right. So first, we have to have y. So the function f of x, let's write using y instead. So we have that. Next, we do these two steps, interchange x and y, and then solve for y. So x and y interchange, we have x equal to 7y plus 2. So that's the first step. Now the second step is to solve for y. So minus 2. So we have x minus 2 equals 7y. And we divide by 2 on both sides, 7 on both sides. That's that is to find the inverse. Next, we will have y equal to x minus 2 over 7. And pretty much it. For cosmetic, we just rewrite using the notation for the inverse. F to negative 1. But we just say f inverse equal to x minus 2 over 7. So much that is the inverse of that function. Right. This one too. So first step, can't have to replace. So we have y. The first step is y becomes x and x becomes y. And then we solve for y. Solve for y's. So get the y by itself. First get rid of the cube. So I will take the cube root on both sides. If we take the cube root on both sides, we don't have to worry about the positive or the negative. If it is the square root, then we have to worry about that. Cube root, an odd root, don't need to worry about that. And then the cube roots and the cube cancel out. So we just have cube root of x equal to y plus 5 and minus 5 on both sides. We have y equal to cube root of x minus 5. And that's pretty much it. Except we use the notation for the inverse. F inverse equal to cube root of x minus 5. So let me update the list. Right, so that is inverse. Find the inverse of a one-to-one function. Right, next, we use transformation to graph an exponential function. First, I just want to get the basic properties of exponential function. So we have the basic function is in this case is 2 to the x power. Right. And the basic of this function, we have two characteristics. The first one, it will go to this point 0 and 1, and the horizontal asymptote. Sorry, I should not use pencil. So yeah, that the point 0 and 1. So the characteristic of exponential function, first, it has the point 0 and 1, and the second part of it is it has the horizontal asymptote as the x-axis, or y equal to 0. So we have a point here, and a line here. Yeah, we cannot, difficult to see right now, but it will become clear later. Anyway, 2 to the x, so it will go like this. Yeah, we just get the sketch, so that is 2 to the x power. Alright, now the transformation, we have quite a few things. First, I would not say first or second, we have the minus 2 here, or the minus and the 2. We have the plus 3, so the plus 3, meaning that the graph will go to the left 3 unit. And then we have the plus 4, will be 4 unit up, or go up 4 unit. And then we have the minus 2. The minus 2 will do two things. First, the minus is reflect vertically. And then the 2 will multiply y values by 2. If we multiply anything by 2, we're going to get the bigger number. It's also, when it's positive, multiplied by 2, we get a bigger number. Therefore, it is a stretch. Right, so we're going to do this. But the order operation says that we're going to do the plus 3 first. So this is the first graph. And after that, the minus 2. And after that, 4 unit up. So we're going to do in this order. So first, 3 unit to the left. This point will go 3 unit to the left, become this point. The horizontal asymptote move 3 unit to the left. We still have the same line. So it will go like that. Next, it will reflect and then stretch, or stretch then reflect. It doesn't matter. So since there are two of them, I'm going to do the first one in the dashed line to reflect it vertically. So the point here will reflect. You will see every time we do this, I keep track of the point. The point move here and then reflect. It is 1 up. When we reflect, it becomes 1 down, and then the graph, say, right, so we have that. Now we stretch. To stretch it, again, first we keep track of the point. The y values of this point is -1. Multiply that by 2, it becomes -2. This point around here, whatever the y value is, we're going to multiply by 2, so it's going to be twice as long. And finally, the graph we looked like that. Yeah, just a sketch. The horizontal asymptote is still the same because it will reflect it. It's still on the same line. Right, and finally, we move up 4 units. So this is -2 originally, 1, 2, 3, and 4. And the horizontal asymptote originally, right now it is the y equal to 0 or x-axis. So 1, 2, 3, and 4. And then just say it go like this. So we have that. So difficult to get all the points correctly, but it's very important we need to keep track of this point. It will follow all the transformation, and the horizontal axis also follow all the transformation. We keep track of those things, and we have the graph. And that's just the sketch of the graph. That's what I expect you to do. But first, we do need to know the basic of the exponential function, which is that. And then we apply the transformation to it. I'll just keep track of those two things. Right. Next, we have to find the values of logarithms. So we have something like this. Before we go to that, let me try to find those formulas. Right. Right. Found it. I'm going to put the formula over this side. Right. So this all the properties of the log that we have. So it's on that side. Right. But the most important is the definition of the log. It is the inverse of the exponential function. So I will write this down. When we have y equal to log base a of x, we can interchange that to x equal to a to the y. What we did was interchange x here and y there. So interchange x and y. The base is still a. and x and y interchange. Right. Now look at the first one. Oh, by the way, there will be quite a few more formulas for the exponential. Right. First, that for those problems I'm going to do in two different ways. First, let's do the long way, but easier. We make this equal to y, I mean to x, because we don't know what it is equal to, and then we interchange. It becomes 4 to the x. So we just swap the 1 over 64 and the x, interchange. So we have 4 to the x equal to 1 over 64. Okay. Now we solve this. 4 to the x, you can write 2 squares to the x, and 64 you can write 2 to the 6 is 64. Now power to another power, we multiply them, so we have 2 to the 2x, and this at the bottom, when you move to the top, we have 2 to the negative 6. Now two things are equal, then the bases will be, the bases are equal, then the exponent will be equal. So we have 2x equal to negative 6, so x equal to negative 3. Right. That is one way to do it. It's long, but it's easy to understand. Try to swap to exponential form, and we have that. Try to make the bases the same, and then the exponent will be equal. By the way, the properties we do here is b to the m times b to the n is b to the m times n. So that's what we have here. And this properties is when we have something divided by b to m positive power, if we move that to the top, that becomes negative m. And this properties allows us to go from here to here, here to here. So x equal to negative 3, that is. Right. So that is the long way. Certainly works. Here is another solution. So when we write log base 4 of 1 over 64, we can write log base 4. By the way, 64 is also 4 cubed. So we can write 4 cubed. And then we use that properties, 4 cubed at the bottom, move to the top. You have 4 to the negative 3. Now, the bases and of the log and exponential are equal. We can cancel. And the properties I use is this one. Yeah, that one. So that cancel. And we have negative 3. Right. Whether we use that properties or we use the long way and change to exponential function, we still the same way. Right. And most of the problem will be that 8. Right. Again, the long way and then the easy, the more direct way. So let's separate this. So first we make this equal to x. So we have log 11. I just copy the problem. I haven't done anything here. What we do is we swap using that property. We have 11 to the x equal to the square root of 11. Right. Next, on the left side, still 11 to the x. What formula we use here? The properties of the exponent. When we have that, we have b to the m over n. And with that, this property will allow us to write square root. By default, we can write it's 1 here. 11 to the first power is still 1. Still 11. And then square root, we can just write the 2 there. So therefore, this is 1 over 2. With that, of course, x equal to 1/2. Right. So that is the long way where we swap to exponential form. Now if we write directly log base 11 of square root of 11, we can write that as log base 11, and then 11 square root of 11, you do pretty much like this. It is 11 to the 1/2, and base 11 and 11 cancel out. Again, the same formula that we still highlight over there. It is just 1/2. Same thing for this problem. But first, where the log that does not have any base, by default, it is the base 10. It's called the common log. 10,000 is 10 to the 4th power because we have 4 zeros. And again, the same properties still highlight there. This is going to be just 4, so those cancel out. Yeah, on this one I did not swap to exponential form because I think that should be easy as we write 10 to the 4th power. Right. Number 10, I'm not going to do that, but we can use this property. Yeah. That property is where in here we can rewrite it as log base e of 1. Of course, any base, log of any base of 1 is going to be 0. Of course, that's the properties we have there. Right. So those are the properties of the logarithms. Next, the domain of logarithmic function. So, when we have the log of any base, doesn't matter what the base is, whatever we put in there has to be positive. So for this, we're going to have -1, negative x, positive. So we solve for x, so get x by itself, so I can just simply add x on both sides here and have -1 greater than that x, or pretty much x less than -1. So that by the way, on the test, if you have something like this, just write the answer there. It is easier to track the letter than actually write the answer, so write the letter instead. Right. So let me update the list. Next, we expand the logarithms. To do that, we use these formulas in the middle here. Right. So first log of this one, we write sum of the difference, meaning this one is expanding. So by the way, we're going to do the expanding and condensing at the moment. So first we have division, meaning that it is a difference. So division is a difference. Right. And next we can write log base 4 square root of x. We can write x to the 1/2 minus that. Actually, we can also write x to the 1/2, and we will take the 1/2 power outside. And the log base 4 of 64, you can write 4 cubed, and the cube goes outside. So we have 1/2 log base 4 of x minus 3 log base 4 of 4. Actually, I should have seen that earlier. We also still have this formula as well, right? So this, I should say, it just cancel out and equal to 3. And those cancel. We should have 3. But then, of course, we also have the formula above it. Sorry. This. Meaning that log base 4 of 4, as long as the base and the argument are the same, that cancel. So that's still 3. So it's 1/2 log base 4 of x minus 3. Right. The next one is easier. Log base b. First we have multiply, so it's going to be a plus, and then we have divide. Right. And also there's important things here. So once again, multiply is add, and divide is subtract. But we also have this. If it's positive, or we just add them, I mean, we put anything on the top is positive. Anything at the bottom, we carry the negative sign. So rather than we split this in 2 and then split in 3, we just do this directly as log base b of x. The y to the 7 is still on top, so we still have positive. The z squared at the bottom, so the bottom will have negative. And then we'll can take the 7 power outside, the 2 outside. And we have that. So that is expanding logarithms. We write a log as many little logs as possible. So we have that. Because when we can simplify, we do that as well. Even we like that to have a bunch of little logs. If we can simplify that, we do that as well. So once again, the formula on that side is there. Also, if we have the positive, that term is on the top. If we have a negative, that term at the bottom. So this will be very handy for the next example. First, yeah, we will just do it into parentheses first, and it is the minus here. So we're going to write log base a. Right. Before the log base a of q, it is positive, so we put q on the top, and then put r at the bottom, because it is negative at the bottom. Right. For this, before we can combine them, we have to take the 6 inside, because when we combine them, we can only combine them if each one of them is one of each log. If we have only one of each log, so one log here, one log there, we can combine positive on top, negative at the bottom. So we take the 6 inside, we have log base a p to the 6th power. Now we combine these two things. We still have q and r. Now the p to the 6th, the coefficient is positive, so we're going to put that on the top, and it's just like that. So this expanding, we have 12 and 13. Right. Next we have exponential equation and logarithmic equation. Right. So there will be two types of equation for each one. The first one is the one-to-one property. So I will write two types here. So type 1. If we have b to the x equal to b to the y, then x equal to y. Pretty much when the bases are equal, the whole thing are equal, then the exponent must be equal. So when the bases are equal, the exponent must be equal. Next, when we cannot do that, then we can always interchange between b to the x equal to y as log base b of y equal to x. So interchange between the log and exponential function, or if we have the bases are equal, then we do that. So when we look at this is base e and that is base 3. There is no way the bases are equal, so we can swap to exponential form. And also besides swapping the exponential form, here's another thing we can also consider, is to take the ln on both sides. So either one of this is fine, we only need to do one. So if we have this one, first I'll do both. First, if we have e to the 5x equal to 3, we're going to take the ln on both sides. The exponents go outside, so we'll have 5x ln of e equal to ln of 3. It just happened that ln of e is log base e of 1. I'm going to write like this. This term is as log base e of e, which is equal to 1. I'm using these properties. of course. I'm sorry, not that. I mean this. That one. So the basis and the exponent are the same, cancel out. So 5x equal to ln of 3. So x equal to ln of 3 divided by 5. So we have that ln of 3 divided by 5. So that is one way to do it. We'll take ln on both sides. Another way is where we have e to the 5x equal to 3. We're going to swap. To swap that, we're going to write log base e, and then we swap this 2. The 3 goes here, the 5x goes there. Log base e is going to be ln of e, I mean ln, and then 3 divided by 5. So we have x equal to ln of 3 divided by 5. So when the bases cannot be equal, cannot turn to something equal, we take ln on both sides, take the exponent down, and then solve for x, or we switch to exponential form. Of course, when the bases are equal, like this equation, we try to make them equal. Not quite equal here, but we can make them equal. And once the bases are equal, the exponent are equal. It's not here, not like that. So we have 15 only. Right, logarithmic equation. Oh, by the way, sorry. Should do one more of the exponential equation. Yeah, we should do 17 as well. So first we have 3 to the 6 minus 3x and 1 over 27. Looks like both of them you can write as the powers of base 3. So we're going to keep that for now. This we have 1 over 3 cubed. 3 cubed at the bottom we bring to the top. And we write like that. And now two things are equal. The bases are equal. The exponents must be equal. So we write 6 minus 3x equal to minus 3. And then the rest is easy. Minus 6 on both sides. And then divide by minus 3. So x equal to 3. Yeah, so pretty much that. Right. Next, logarithmic equations. Logarithmic equations, that's different, but there are also two types like exponential equation we have earlier. So let's write that out. There will be type 1 is where we have both of them log of the base are equal. Then we say x equal to y. So that is one type. The type 2 is where we have log of something, but it is equal to a number instead. So that is missing a log. So just like this problem, there's the number by itself. Alright, in that case, we will switch to exponential form and we say b to the y equal to x. So those are the two types of logarithmic equation. Except there will be one more thing to worry about, is the domain of the logarithmic function. Just need to make sure that whatever we put inside a log has to be positive. So keep that in mind as we do the problem. Right. And also those, not that. Those properties will come handy. Right. Now, run the first one. We saw that already. First, we have a plus sign here, meaning that it is going to be multiplying. By the way, this problem we do not have the base of the log, which means this is the base 10. Whether with the base 10 or not, let's put the base 10 here. Since both of them have the same base on both sides, we can cancel. And we just have 3x equal to 4x minus 1. Multiply it out. 4x minus 4 and minus 4x. We have x, negative x equal to negative 4. So x equal to 4, positive 4. Almost like that, except just need to check for the log must be positive. So we do not have the conclusion yet. So we check at x equal to 4. We're going to put 4 in for x. That is multiply log base 4 minus 1. Now we see that this is positive, which is good. That is positive, it's good. Is also positive, it's good. So we confirm that every log, everything inside of each log is positive. So that solution is good. So we say x equal to 4 as is the solution. Right. So that is where we have the logs everywhere. So in that case we have one log on each side, and we make them equal because the log of the bases are the same. Right. This problem we cannot do that simply because we have the 4 by itself here, so we cannot do that. Instead, first we have the plus sign here. So that log base 3 of x multiplying x minus 24 equal to 4. Again, there's a number by itself. So if there's a number by itself, we have to swap to exponential form, meaning that we're going to write 3 and the equal sign, and then we swaps x times x minus 24 and 4. Let's just say 4. So 3 to the 4th power is 81, and that x squared minus 24x. Rewrite this, we have x squared minus 24x minus 81 equal to 0. So minus 81 on both sides here. Right. Now we just need to solve for that. Right. I'm not sure my calculator has that app. Nope. Right. So I have to actually use this. Right. So we have that apps where we hit application. Of course, this is too simple. We can do it by hand, but just make sure that you can also use the calculator to simplify things. So we look for that app and polynomial root finder. That's the first option. We're looking for the second order of quadratic equation. Once it's done, now we operate using the lower menu. So hit next here. The coefficient is 1 minus 24. Notice the minus is this key and not that key. And then minus 81. Oops, sorry. And then we hit solve. Like I said, operate using the lower menu option. And we have 27 and minus 3. So we just say x equal to 27 and x equal to minus 3. Of course, you can do it by hand also, but I'm kind of run out of space. Anyway, so we need to check both of them. First, at x equal to 27, we have log base 3 of 27, log base 3 of 27 minus 24, and equal to 4. So what we say is that this is positive, which is good. Positive is good. So every inside all the log are positive. So that solution is good. We have x equal to 27. Now we check for x equal to negative 3. So we put negative 3 in for x. We should stop here already because right on the first one it failed. It's negative, which means it doesn't count. So we only have one solution here. It's x equal to 27. So where we have log on both sides, try to combine to have one log on each side. So we combine them, one log on each side, cancel out. That's easy. When we don't have the log on both sides, in particular when we have a number by itself like this, we have to swap to exponential form. And when we do solve for it, at the end always have to check for the logarithmic equation. So always have to check. Right, find trigonometric function values. By the way, we're done with the formula over there, so I'm going to take it out. Right. Right, so you see something like this. So first we have the cosine is 4 over 9. So let's try to draw a triangle. Cosine we do know is 4 over 9. Cosine is adjacent over hypotenuse. Adjacent over hypotenuse. So that pretty much x equal to 4 and r equal to 9. Then we have y. Need to find the missing length. So we have x squared plus y squared equal to r squared. 4 squared for x, y squared, r squared is 9 squared. So y squared equal to 81 minus 16. A1 minus 16, so 65. Alright, and then we'll take the square root on both sides, which gives us plus or minus square of 65. It's very important that we have the plus or minus when we take the square root. Right. Next, we determine if it is a positive or negative, meaning we choose the plus or the minus. So we look at the problem. We have cosine is that. Next, tangent is negative, meaning we have, actually we don't even need the graph. Tangent is negative, right? Tangent is opposite over adjacent, and that one is negative. Let's see what we have. We have x is 4, so we know x is positive. So y over a positive have to be negative. So what do you think? If y divided by a positive number is negative, then y must be negative. We need one of the y over x to be negative. Since x is positive, y is negative. So we're going to choose the minus, because it is in it makes this negative, right? So we say equal to negative square of 65. And finally, our question answers for sine. Sine of theta is opposite over hypotenuse. Opposite is y, which is negative square root of 65. Hypotenuse is 9. Since we have a lot of this, actually I should just do one more then. So next, tangent of theta equal to negative y over x. So I will draw the triangle again. Tangent, it is negative, so one and tangent is y over x. So one of this has to be negative, but we do not just say that y is negative 10 and x equal to 7. That would be wrong, because we don't know anything about x and y yet. What we do know is it is in quadrant 2. So now we're trying to draw it in this quadrant. If it is in this quadrant, then x is negative and y is positive. If it is in this quadrant. So because x is negative, we're going to take the negative and keep that with the x. So we say x equal to negative 7 at the bottom, 7 but with the negative, and then y is equal to positive 10. Because in this quadrant y is positive, so we take the negative away from the y and put that on the x. So we have that. So y is 10, x is negative 7, and we can find the r. Negative 7 square plus 10 square equal to r squared. That is 149. And then we'll take the square root on both sides. So r equal to plus or minus square root of 149. The good thing about the r is always positive. So we're going to choose positive. And once we have x, y, and r, we just find cosine pretty easily. So we have cosine of theta equal to x over r. We have 7 over square root of 149. Yeah, we start with a trig function that we know and try to find the missing length. Once we have the missing length, we can find the remaining trig function, all of them if we need to, but we only ask to find one. So that is 21, 22. Right. Next, find exact values of a trig function. You need to know to do this. So first, I'll just do one here. Just get the idea. I will determine two things. First, if that's positive or negative. 5 pi over 3. Let's see. We have 0 pi over 2. This is a pi. And 3 pi over 2. Or 1.5 pi. If we're not very confident with the fraction and the pi, just do it like this. 5 divided by 3. So basically, we throw away the pi, ignore the pi, and we have 1.667. Here 3 pi over 2, and which is 1.5. So we have pretty much in quadrant 3. In quadrant 3, we have x is positive, y is negative, and r is always positive. Sorry, I have the calculator on the way. There. So this is in quadrant 3, and we have this. X positive, y is negative, and we have sine is going to be equal to y over r. So it's going to be negative. Yeah. And then next, we just find the reference angle. And the reference angle, the way we do that is, if this is divisible by 3, divided by 3, then we just say the reference angle is pi over 3. So we have negative sine pi over 3 is square of 3 over 2. And that's pretty much that. So just need to determine two things. What quadrant it is. That will tell us if it is positive or negative. And next, the reference angle. The reference angle is whatever it is divided by the same number. So I would say the reference angle of this problem is going to be pi over 6. The reference angle of this problem is 45 degrees. Right, so we'll do 26 instead. Second, by the way, it's in the first quadrant, so it's positive. Second is 1 over cosine 45 degrees. And cosine 45 degrees, square root of 2 over 2. And divide fraction is multiplying reciprocal. So we just live with that. Or just square root of 2. Right. We can also have something like this, where we have to minus 360 or minus more, or add to 60 to get the angle between 0 and 2 pi. And then we find the reference angle to find the values. Reference angle give us the values. The quadrant give us the sign. So quadrant 3, y over r is going to be negative. Right. Right. Next, we find the exact values of the inverse function. So on this, if you memorize, good. If not, if you use a calculator, make sure it is in the degree mode. So hit mode, and I keep that as degree. Now I just hit cosine inverse. Of course, by second cosine give us cosine inverse of negative square root of 2 divided by 2, right? It is 135 degrees. Wait, it's here. And we multiply pi divided by 180 to change to radian. And that gives us 3 pi over 4. 135 divided by 180. So and you can change to fraction. Right. So that. Right. Next. Right. Let me write this out first. There's 25, 26 there. So 25 and 26. This one as well, and that is number, sorry, 25 and 26 is here. So once again, I should say the reference angle of will have kind of the same multiple. Like if we have 3, so it's going to be pi over 3. If we have divided by 6, it's going to be pi over 6. If we have divided by 4, that will be pi over 4, and so on. And then 29 inverse, so that's pretty much that. We have 29. Right. Next, the computation of the trig and the trig inverse trig function. This is very interesting. The easiest part is if we have the function and the function inverse, that will guarantee to cancel if it is defined. So I'll write first. So cancel if it is defined. So when we do that, that is where we have a function and the inverse. So we have a function outside and the same inverse function inside. We can cancel like that, but it has to be defined. And so if we use the enter that in the calculator, make sure it is in the degree mode. Right, next, this one is always defined. But not cancel. Every time. Right, so in fact, if you put in the calculator, it will show that it doesn't work. Right, first, right, let's see. We have 4 pi over 7. Let's do this. I can use the calculator. Right, first, let's just type exactly what we have. We do need to keep this in the radian mode when we do the computation of the function in the inverse. Right, so sine inverse of sine of, I put 4 pi sine inverse and then sine, and then alpha, then the fraction 4 pi over 7. Right, and we do that. We have 1.3461. Right, now let's do 4 pi divided by 7. We have a fraction here, 4 pi divided by 7. Delete that. So you see, the actual answer is less than that. 4 pi over 7 is 1.79, so it doesn't cancel here. Right, so that has to refer back to the domain of the trig function and the inverse function, I mean. So first we have 4 pi over 7 is just about here. So we're going to have to reduce that into first and second. So this side inverse here, the domain and range, the range domain must be between negative pi over 2 and pi over 2. I'm sorry, that was the range. So the domain of the sine function, but this is the range for the inverse, negative pi over 2 to pi over 2. And with 4 pi over 7, it's just a little bit more than pi over 2. So in that case, we have to find the reference angle. The reference angle is going to be this. If the whole thing is pi minus 4 pi over 7 is this one. So we have 4 pi minus 7 is equal to 3 pi minus that is 3 pi over 7. So we find the reference angle for 4 pi over 7. We get 3 pi over 7. And that's why when we cancel this, it does not cancel, but it will give us the reference angle. Because both the side values are going to be positive, so we just use the reference angle. And that 3 pi over 7. Right. So the function cancels the inverse. But not the other way around. It cancels if it is defined. The other way might not work. Right. So that's not really important. What more important is 33 and 34. So those kind of things where we combine the function and the inverse. So we do have 30. Right. Focus on 33 here. So what we see, first we let inside part equal to theta. And then we will take the same function we have cosine first, and then inside is cosine inverse of 1/3. We take cosine on both sides. The function always cancels the inverse, so that cancels, which is good. So we have 1/3 and cosine of theta. So that's what we have. Of course, when we have that, we can draw a triangle. Cosine is adjacent over the hypotenuse. So hypotenuse is 3, adjacent is 1. Just need to find the missing length here. So this is going to be y, so 1 square plus y square is 3 square, so y square is equal to a square, or y equal to plus or minus square root of 8. Remember, there's a plus or minus, and that to be determined or not, it doesn't matter. We will see why in a minute. Right, next, let's put in the calculator and see what do we have. What I'm trying to see is the cosine inverse. When we do the inverse by itself, it's better to keep in the degree mode. If we want to do the whole thing radian mode, but if we only do the inverse, I will keep in the degree mode. It is easier to see where it is. So cosine inverse, only cosine inverse of 1 over 3 is 70 point something. So it is in the quadrant 1. So we have tangent of the quadrant 1. Quadrant 1. Of course, anything in quadrant 1 on the trig function is positive. So we know the end result must be positive. So that's what we know. So whether we choose the plus or negative here, not really important. Right. Next, what we're trying to find is tangent of the cosine inverse of 1/3. And the cosine inverse of 1/3 is theta. And we do know that whatever it is at the end is going to be positive. So tangent of the theta is opposite over adjacent, and opposite could be y, could be plus or minus square root of 8 over 1, and whatever we choose here has to be positive. So it's going to be square root of 8. Right, so we have that. This is important, so I do one more. Where's the list? Oh. Right, 34. Same thing here. Let inside be theta. We'll take cosine on both sides. That will not do. Have to take the sine on both sides. Sorry. Just the sine. And then we cancel. The function always cancel the inverse. So we have sine of theta equal to u. We can also write u over 1 because we do need to have a ratio. Right. Sine is opposite over hypotenuse, and we don't have this, so we have x squared plus u squared is 1, so x squared equal to 1 minus u squared, and to get rid of the square we take the square root, and there's the plus or minus. And now we need to determine if it is positive or negative. this might be a little trouble. First, the sine inverse. The domain is only in the quadrant 1 or quadrant 4. So again, let me write that down. I should say the range. Do that again. Quadrant 1, quadrant 4, 104. So we're going to have cosine of quadrant 1 or quadrant 4, cosine of those quadrants here or here. The x value is positive, so it's going to be positive, and we choose positive. Actually, that's not the reason, right? Anyway, so we have cosine of sine inverse u equal to cosine of theta will be opposite, adjacent over hypotenuse, so it will be just x over 1, which is plus or minus square root of 1 minus u squared over 1. And of course, since the whole thing is positive, we choose positive here. So pretty much that. So just determine what is the range of the inside, and then we know the sign of the whole thing. Usually it's going to, in this case, positive, but that's how we do. So we take theta equal to inside function, set the ratio, and find the triangle, find all the length, and then after that, find the different trig of that theta, and we have that. The sign is not very important here, but we can determine pretty easily. Right. Sorry, I have to start a stream again because the earlier video frozen in the middle. At least we have most of it done, but I have to edit the last part. So I have to do the last part of the section again about the trigonometric equation. So we look at number 35. Right. So the formula says on that side. So for sine, we have the supplementary, meaning that other than the inverse, we might have the inverse, the supplementary, meaning we subtract from pi, plus 2n pi, that is the standard period of sine and cosine. For cosine, we're going to have opposite, so sine is supplementary, cosine is opposite, still plus 2n pi, and tangent, there is no thing for tangent, but also for tangent the period is just pi, so we just have n instead of 2n like every other trig function like sine, cosine. Right, so we have 35, and this is part where I have for the video earlier, and it's frozen, so I have to I still have this anyway. So we have that. So to get back to theta, we take the inverse of sine, and we have that, and the supplement, meaning subtract from pi, and have that. So sine inverse of square of 3 over 2, use a calculator for this. Not that. Alright, that. So if I use inverse a trig function, if only the inverse trig function by itself must be in degree mode. inverse sine of square root of 3 over 2, and that is 60 degrees, which is pi over 3. And because we know this is pi over 3, move the calculator over here. Now, this is pi minus pi over 3, so I will not use pi, I just use 1 minus 1 over 3. We have that, change the fraction, and 2 pi over 3 plus 2n pi. Right. Next, what we'll determine is, let me put the calculator away. What we determine next is, actually no, that's all we do. It is problem because we have all the solution, and with all the solution we're going to have just plus 2n pi to it. So that's it pretty much for 35. Right. We're going to go to 36. Right. The difference between 35 and 36 is that solution for 36 must be within 0 and 2 pi. That is important. Right. This might take a lot of space, so I try to write very small. Even then might not be enough. Anyway, so I have cosine, so that will be the angle inside 2x minus pi over 2 equal to cosine inverse of square root 2 over 2 plus 2n pi. Now cosine, unlike the sine, is opposite, so we're going to have opposite of this as well. Right. So first I'm going to add pi over 2 on both sides. Cosine square root 2 over 2, if you do the inverse, that would be pi over 4. So we have 2x minus pi over 2 and then plus pi over 2 on both sides. By the way, I have to delete this to get more space. Erase that. Wish I could. Right. 2x equal to pi over 4 plus pi over 2. I can put that here. Right. So we have just have 1/2 plus 1/4. So that gives us 3 over 4 pi plus 2n pi. Or this, we have 1/2 minus 1/4. We have 2x equal to, change that to fraction, 1 over 4 or pi over 4 plus 2n pi. Right. And then we divide by 2 both sides. So we have x equal to 3 pi over 8. 2 and 2 cancel, that's just n pi. Sorry. That x equal pi over 8. And 2 and 2 cancel again, plus n pi. Right. Now, the difference between this one and the next one and the previous one is that this one, the solution between 0 and 2 pi. I will find the length for that. By length I mean the distance between 0 and 2 pi is 2 pi. The period for this problem, it is just a pi. So the length is 2 pi, the period for this problem is a pi. So I take the length divided by the period. Two pi divided by pi is 2. So we have 2. And what that stands for? That means 2 will give you 2 values for n. It is like if we have the solution that is between 0 and 2 pi, and the solution only pi apart. So if you have choose here and you take pi distance from it, surely we're going to have another values. If the distance for the solution is just a pi, doesn't matter what point you choose inside, there will be always another point in it. So that's why we have 2 values for n. So the length divided by the period gives us the numbers, 2 values for n. So in that case we have to choose. Right, now we choose. We have 2 solutions here. So that and that. When n equal to 0, we have 0 for n, and we have 3 pi over 8. 3 pi over 8 is between 0 and 2 pi, so which is good. We have one solution. Next, for this, we have n equal to 0, we have pi over 8, which is also between 0 to 2 pi, so that is a solution. Next, we choose n equal to 1. 3 pi over 8 plus pi, because n is 1, so 3 pi over 8 plus pi, and use the calculator here. Three over 8 plus 1, change that to fraction, 11 over 8. And that is still between 0 and 2 pi. We know that is between 2 pi because it's just 1.375. So it is good. We have 2 values for n for this, so we're good here. We're good for that equation. Now we're going to go for this one. We have 1 already. Now if we have pi over 8 plus pi, because when n equal to 1, and that gives us, let's do that. So 1 over 8 plus 1. So we not just do this to get the answer. We do this, we know that is 1.25, which is still between 0 and 2 pi. So change the fraction, 9 over 8, so 9 pi over 8. This is, of course, is equal to 1.125, which is less than 2 pi. So that solution is good. And we have 2 values for n for this one, and 2 values for n of that one. So that's all we have. Right, so that is the cosine inverse. For this one, in order to do this, 38, we have to write that as the inverse of reciprocal of sine, and then we can only solve for sine, cosine, and tangent. So need to convert that to sine. I think I'm going to do this one as well. Right, so again I'm going to have we don't have a lot of space here, so just skip a few steps and we solve for cosecant. So we should have cosecant of x minus pi over 6 is equal to 2 over square root of 3, and cosecant is 1 over sine, and reciprocal, so we're going to flip both sides. Now we have a trig function, a trigonometric equation. Right, for sine we're going to take the angle with the inverse, or the supplementary. I don't know why right over 2 or 6. Supplementary is pi minus sine inverse plus 2n pi. Right. So I'm going to add pi over 6 on both sides. Right. Sine of inverse of 3 over 2. I think we did that earlier. That's pi over 3. So I have that is pi over 3 plus pi over 6 plus 2n pi, or x. This also add pi over 6 on both sides. And we have, okay, pi minus pi over 3. We did that earlier as well, 2 pi over 3. So that inside the square bracket is 2 pi over 3. And then we plus pi over 6 plus 2n pi. Right. Now we get the calculator again. Right. Pi over 3 plus pi over 6, so 1 over 3. 1 over 3 plus 1 over 6 is 1/2. So x equal to pi over 2 plus 2n pi, or 2 pi over 3 plus pi over 6, so 2 over 3 plus pi over 6. And that is 5 pi over 6 plus 2n pi. Right, next. Similar to last problem, we want the solution between 0 and 2 pi, so the length is still 2 pi for this problem. For this problem though, the period is 2 pi. So length divided by the period is 1. So that is 1 is the values for n. So we just have one value for n. Right, now we choose. Usually we just choose 0 for n. When n equal to 0, we just have pi over 2, which is good because pi over 2 is between 0 and 2 pi. Now, when n equal to 0, on this side, we have 5 pi over 6, also between 0 and 2 pi. And since we only require to have one value for n, that's all we have. So those are the solution. Again, those formula will be very useful. Right, I think I'm going to stop here for the review. So I hope this helped you to prepare for the test on Monday. Thanks for watching.